guys at home, can I get a thumbs up that you hear me and see the board okay? Awesome, here we go. So we are starting section 8, which is very similar to section 7, but instead of like showing how our money can grow at an exponential rate, now we're just gonna look at like living things, cells, radioactive decay, populations can grow at an exponential rate because these are all things that are growing in proportion to their own size. So the bigger the population gets, the faster it can get even bigger. The smaller something gets, then the faster it can get even smaller because it's all in relation to its own size, all right? And that's how exponential growth and decay works. So we're just gonna give you, these are all things that are basically growing at a constant rate. So it's gonna be basically just a twist on the PERT formula for our money, all right? So here we go. Just like money can grow continuously, so can other natural phenomenon demonstrate uninhibited growth or decay. Some examples are cell division of many living organisms, which demonstrate the growth process, and radioactive substances that have a specific half-life and demonstrate decay. So let's go over the formulas. Guys, they're literally going to be just like PERT. We're just going to change up the variables, all right? So if you are something that follows the law of uninhibited growth or decay, something that is growing at an exponential rate or decreasing at an exponential rate, then your formula is going to be A of t equals A sub 0, which is your P, it's your start amount, times E to the, I think they use KT, where K is going to be your growth rate and T is going to be the time. But go ahead.
Is K capitalized?
K? I don't know. I think it's a lowercase k. I don't think it'll matter. You'll see it in the problems. All right? But the time now, a lot of times with money, your time had to be in years. In these problems, you really have to pay attention to the problem. Are they talking about days, weeks, hours, minutes? The time can be all over the place. And you want to make sure whatever the time is, that's the kind of time you're plugging in. All right, where A sub 0, guys, that's going to be your initial amount, your start amount. So if the population of bacteria started at 100 grams, that's your A sub 0, your start amount. And K, this rate of growth, can't equal 0, and it is a positive constant. And it is known as your growth rate. Okay? Well, I don't know why they do this, but they do. I feel like it's a little redundant. But then they take this uninhibited growth formula and they apply it to the growth of cells directly. And he gets a new formula. But it's the exact same thing, except we just changed the variables. So it's a little confusing, I get it. But they're all showing that this is a continuously growing population. So if you are the growth of cells, a model that gives the number of N of cells in a culture after a time t has passed, then we use this formula. The amount after time t will be equal to N sub 0, where N sub 0 is your initial amount, times E to the KT. So they just changed all of the A's to N's. I don't know why. To me, it's just another formula for you to memorize, but it all means the same thing. Where K is greater than 0, N sub 0 is your initial number of cells. And K is that positive constant that represents that growth rate.
Positive constant and growth rate are like
It's the same thing. It's going to be the same number throughout the entire problem, and it'll be a positive number. Usually a decimal because it represents a rate or a percent. So guys, it may sound like, well, I don't really know a lot about cell division. Me either, but the formulas are very usable. So look at example number 1. All right. A colony of bacteria grows according to the law of uninhibited growth. That means you can use one of these formulas to model its growth. According to the function N of t equals 100 times e to the 0.045 t. So they've given you a pre-written formula for the uninhibited growth of this, bacteria, where N The number of bacteria is measured in grams, and T is measured in days. That means you only want to plug days into this function for T. In part A, determine the initial amount of bacteria. Guys, look at the formula. In this pre-written formula, which one of those numbers represents the initial amount of this bacteria? The first number, right? The A sub 0, the N sub 0, if you will, the P, the principal from PERC. Just like you get this formula, you know it started with 100 grams of bacteria. Then it says, what is the rate of growth of the bacteria? Guys, we know the rate is equal to K, and we know in the formula it's K times T. So 0.045 is your growth rate, which as a percent would be 4.5%. So guys, that means this bacteria is growing 4.5% of its population each day. All right, what is the population after 5 days? Well, if T is 5, what's the number of bacteria going to be? Let's plug in 5 for T and ask our calculator to do this. They're asking you to find N of 5, because T is 5. All right, so that's going to be 100 times e to the 0.045 times 5. Ask your calculator. I don't know what it's going to tell us to round to, so we'll round to like 1 decimal place, but just check your homework. I wrote this down. And when you ask your calculator, you should find out that there's 125.2 grams of bacteria after 5 days. Started as 100, went to 125.2 after 5 days. Okay, well now it's asking, how long? So guys, that's a time. They're asking us to find the time. How long will it take the population to reach 140 grams? So guys, they're telling you the end amount. They're telling you this formula has to equal 140. So take your formula, 100 times e to the 0.045 t, because we don't know t, they've asked us to find t, and they want to know when is this going to equal 140 grams? When does that end up being the end amount? So now we have to solve this for t. Guys, t is in the exponent, which means the way to solve for a variable in the exponent, we're probably going to need a lot. All right, but let's get the exponential part by itself. E to this power, let's get the 100 away. Let's isolate the base. And we're going to get e to the 0.045t equals 1.4. All right, now it's like, all right, how am I getting to t, right? It's a base e exponential. Let's natural log both sides. And remember, the natural log has an assumed base of e. So a base e log and a base e exponential cancel. You're just left with 0.045t. And it equals the natural log of 1.4. And then the only thing we have to do to get t by itself is divide by the 0.045. So guys, there's going to be tons of decimals involved here. Be careful what you write down, because it's easy to like all of a sudden just write 0.45 or something, and now your answer is wrong because of a silly mistake. And this will be, we're going to have to round it, about 7.5 days. Just pay attention to what they ask for on the homework. What should we be rounding for?
This is an estimate, not the exact number.
Exactly. Roughly 7.5 days. But the worst thing you can do is take the natural log of 1.4, estimate that, and then divide that estimation by 0.045. Don't do that. Do not estimate until the end of the problem. And again, we're going to be forced in the next example, but I'm going to try and keep as many decimals as I can. All right, last one. What is the doubling time for this population? So guys, they want to know how long. So again, we're looking for a time. Is it going to take this population to double in size? Well, what size did it start at? 100. So they want to know, when is it going to be 200? When is it going to double? So we're going to do this exact same thing, but now we want to set it equal to 200. When's it going to equal 200 as the end amount? So when will 100, we want 100 to go to 200, right? We want it to double. All right, and then I'll solve it, you solve it, we'll end here, let's see what answer we get. Everybody solve this for t. It should be just like this. Isolate that base, natural log both sides, and divide. And then you can check your answer with mine. Yeah. Yep. Are you guys okay? Did everybody get 15.4 days? Thumbs up at home, we're okay? All right, awesome. So again, they're very similar to our PERT questions. The formulas are very user-friendly, and it kind of happens to be the same thing over and over again in the solving process. All right, let's step it up a notch in the next example because they're not going to give us the information that we really want. So first we're going to have to find something that we need, and then we can answer their question. So look at example 2. This is how I feel like they can make these problems a little bit harder when they just don't tell you everything flat out. Okay, this one says, now they're not going to give you a fully pre-written equation for us to use. That's the best case scenario. They just give us the formula, we'll just use it, right? There's going to be missing information that we're going to have to fill in. A colony of bacteria increases according to the law of uninhibited growth. That just means that we can use that formula to write a function. According to the formula on the previous page, if n is the number of bacteria in the culture and t is the time in hours, then we can use this formula. Part A, if 10,000 bacteria are present initially, so guys, clear as day, that's n sub 0. So we're going to be able to plug that right in, that's our initial amount. And the number of bacteria, it doubles in 5 hours. How many bacteria will there be in 24 hours? So guys, that's the question. How many bacteria will there be in 24 hours? The problem is, we don't have the growth rate. We do not know what rate this is growing at. But they gave you enough information to find it. They gave you the initial amount, then they told you the time it doubles in. So they basically told you a time frame it takes to get to an end amount. We're going to be able to use that to calculate our own growth rate. All right, so let's plug in what we know. Right now we know this. N of t equals n sub 0 is 10,000 times e to the kt. Here's the problem. They never flat out told us k, and we clearly need k as our variable. Time is the one we plug in for, so he's the variable that stays. K needs to be a number. So guys, before we can answer the question about 24 hours, we got to figure out k. So we need k. But they gave us information to find it. They said it doubles in 5 hours. So that means it's going to go from 10,000 to 20,000 because it's going to double in 5 hours. Let's do that. Let's plug in 5 as the time. Let's let the end amount be 20,000 and we'll solve for K, the rate of growth. All right, so the end amount is going to be 20,000. That has to equal 10,000 times e to the K times 5, because we know the amount of time it took to double. All right, now let's solve that for K. So let's isolate the base, divide by 10,000. And we're going to get 2 equals e to the 5K. Let's take the natural log of both sides. and you're going to get the natural log of 2 equals 5k. And then to get k, divide by 5. So the most accurate answer for k is the natural log of 2 divided by 5. But if you plug that into the formula, oh my God, does the formula get messy? You're going to be like constantly wondering, am I typing things incorrectly? So we are going to estimate k. The homework may tell you a specific number of decimal places to keep. I'm going to try and keep a lot. All right, so k will equal, because obviously the more accurate k is, the more accurate the answers that we find to this problem are. All right, so I wrote this down. When you get this, k is going to equal, I'm going to say I kept 6 decimals. 0.138629. That's what I kept as k. So now let's plug that into the formula, and now we'll have a working formula. So now we know N of t will equal 10,000 times e to the 0.138629t. We now have a working formula where t is in, what did they say, hours, and then N of t is that end amount of your bacteria. All right, so guys, now we can answer the question. How many bacteria will there be in 24 hours? So now you just plug 24 into the formula. Time is in hours. They gave you 24 hours. Now we just plug in 24 for t. Plug that into your calculator and get me a amount of bacteria. Again, I'm assuming your homework is going to be much clearer about the number of decimal places to keep. All right, I got 278,573.2645. And again, you're just measuring the number of bacteria. So that's the number of bacteria present after 24 hours. All right? Okay. Then it says in the next part, how long is it until there is 500,000 bacteria? So again, they've asked you to find the time. How long until there is 500,000 bacteria? So now we just have to set this equal to 500,000 and figure out the time. So you guys do that there, I'll do it up here, let's see what answer we get.
And this is with that decimal that we found.
Yeah, you're using this 0.138629 the whole time, that's our K. I don't have a lot of board space for this. Let's see if I can fit it up here. I mean, the solving is very repetitive. You divide by a number. You natural log both sides. You divide by a number. It's very repetitive. Let me see again. And remember, keep track of what your time is measured in. This time we're measured in hours, not days or years. This is hours. So when I solved this one, I got 28.2 hours roughly it takes for this population to grow from 10,000 to 500,000. All right, people at home, how we doing? Everybody good at home? Everybody all right? All right. All right, I'm gonna start the decay. Again, it's very similar in the sense of the formulas, except now you're gonna want your initial value to decrease, not increase, all right? So something has to happen to the exponent to make the value go down and not up. So let me at least start this. I don't know how far I'll get. I didn't make our homework due until Wednesday, just in case we didn't get through all of this. I could still finish tomorrow and keep working, and you'd still have time to complete homework problems that maybe you couldn't answer because I haven't gotten to that example yet, all right? But I'm gonna try to keep going a little bit, and then I'm gonna have to stop. I only have 7 minutes. I might be able to get this one example in. I'm gonna leave that just in case anybody's still writing that down. Let me get fresh. All right, here we go. So here's the uninhibited decay. So it says the amount A of a radioactive material present at time t is given by this formula. So now we're going to go back to A sub 0. So the amount after time t will be A sub 0 times E. But guys, now we want the amount to go down, right? This is decay. So now instead of KT, you need negative KT. You need a negative exponent to make the size of this population go down and not up. And that gets a little confusing, and I'll tell you why. Where K is a number less than 0, it's a negative number, right? It represents a decay rate. The amount should be going down. Where A sub 0 is the initial amount, and K is a negative number that represents the rate of decay. But here's the thing. The rate of decay is a negative number in the formula. But if they ever ask you to find the rate of decay, when you talk about the rate, it's like, oh, the decay rate is 2.7%. You talk about it as a positive number. But when you use it in the formula, it's a negative number. So if the homework ever asks you to find a rate, yes, K is a negative number, but I'm pretty sure they mark you wrong if you write it in as a negative number when you speak about it. So when you speak about it, it's a positive number, it's a decay rate, but to use it in the formula, it's a negative number. We learned that the hard way the first year we were using this book, because we were always typing in a negative answer, but they were looking for just the actual rate when you're talking about it, and it's not a negative number. It's a negative number in the formula, if that makes any sense. All right, note, all radioactive substances have a specific half-life, the amount of time it takes them to cut their population in half, which is the time required. Oh, there we go. All right, here we go. Look at number 3. Iodine 131 is a radioactive material that decays according to the function right there. So guys, it looks like the only thing they've given us is the actual decay rate, negative 0.087. So it's a negative number in the formula, but if we were going to speak about it, we'd be like, oh, the decay rate is 8.7%. You know what I mean? All right, where A sub 0 is the initial amount present and A is the amount present at time in days. So now our time is in days. Assume that the scientist initially has a sample of 200 grams of iodine 131. So there's our A sub 0. Let's plug it in right now. So A of t will equal A sub 0 is 200 times e to the negative 0.087 t. It wants to know, what is the decay rate of iodine 131? Well, guys, look in the formula. That's K. So, like I'm saying, it's negative 0.087, but when you talk about it, K is equal to negative 0.087 is negative 8.7%, but I'm telling you, I'm like 99% sure your book, when you write it in the answer of the online, you're just going to put in 8.7%. And maybe I'm wrong, this is a new edition, maybe they fixed that because it did cause a lot of problems. So I apologize if you get that one wrong. Initially, you should be able to fix it. I should have checked that before I assigned the homework, and I forgot.
Negative percent exists.
Not necessarily, other than something, a percent that is going down in value, but depreciation rate can be thought of as negative.
Oh, and this is sort of like a depreciation.
Yeah, it's decaying, it's going down in size. Okay? And the only way to use a formula to make it go down is to have a negative exponent to make it go down.
So if it says like in a problem, like
what is the rate when you're speaking about it?
Yeah.
You would say, oh, it's 8.7%. You don't speak about it as a negative, but you use it as a negative.
Like iodine is decaying at 8.7%.
and it's per,
in the center.
exactly. Okay, so how much iodine 131 is left after 5 days? So guys, just plug in 5. 5 days, days is the unit of time, plug in 5. So we're finding A of 5. So that'll be 200 times e to the negative 0.087 times 5. And I got 129.45 grams. Okay, I'm gonna have to stop after this one and see if we can just finish this. When will 100 grams of iodine be left? So now we wanna find out the time it takes for the iodine to get all the way down to 100 grams. When does it end at 100 grams? Well, guys, think about this. It started at 200 grams. So when you find out when it's 100 grams, you're finding the half-life. You're finding the amount of time it takes for the population to be cut in half. You are literally finding the half-life right now. All right, so set it equal to 100 and solve. Now guys, I would make it easier on yourself. Instead of a half, put 0.5. 0.5 is a lot easier to use on the calculator, and it doesn't sacrifice any rounding. 0.5 and 1/2 are exactly the same. If it was 1/3, you'd have to use 1/3. And it was roughly I got about 7.97 days. So it roughly means the half-life is almost 8 days. So about every 8 days, this population will literally be half of the population. All right, are you guys okay at home? Everybody okay? Awesome, are you guys okay? Everybody's good? All right, so again, very similar. The formulas are very user-friendly, okay? All right, we'll pick this back up tomorrow with the exact same notes. If you want to start your homework, I'm sure there's problems in there that you can do. But I apologize if we get to a couple that I was hoping to get to the next example. So just hold off on those ones. If they get confusing, I'll finish that problem tomorrow, and then we'll go from there, okay? Again, this homework isn't due until Wednesday anyway. All right, let me double check the attendance. I didn't take it.